Hello friends, today in this video we are going to discuss about fundamental theorem of calculus for line integral. So integral gradient of f into dr bar over the contour C is equal f of p1 minus f of p0. So here C is nothing but contour. It has two ending point p0 and p1. So that means this line integral is depend on path p0 and p1. So let us see its first proof. Integration c f sub x dx plus f sub y dy. This can be written from grade f into dr bar. As we know that grade f can be written as del f by del xi plus del f by del yz, and dr bar can be written as dxi plus dyz. But when we take its dot product, so we have f sub x dx. That means del f by del x into dx plus f sub y. That means del f by del y into dy. But as we have studied in first semester, so this is what total derivative, as we can assume df. So line integral df. But as we know that line integrals depend on two endpoints, so we have f of p1 minus f of p0. If we consider another way, so in that case, integration grade f into dr bar, this can be written as we have assumed this, so we can write this way. So here contour C we can represent as a parameter t. So x can be written as x of t and y can be written as y of t at t from t0 to t1. But here small x and small y, the small x can be written as x of t. So dx can be written as x dash t into dt. Same way for y. But when we put all these value here, so what we get? Ln integral over c fx dx can be written as x dash t. But this is what exactly dx bar dt and dt as a common. And fy same, and dy can be written as dy by dt. But as we know, this is what exactly total derivative df by dt into dt. But if we integrate with respect to t, so what we get? But as we know that one result, integration and derivative both are inverse of each other. So we can say f of x of t and y of t over t0 to t1. But when we put t is equal to t1, so what we get? F of x of t1 minus comma y of t1. But here x of t1 y of t1 is point p1, so we can represent f of p1 minus f of x of t0 minus y of t0, so that is point p0, so we can say f of p0. So ultimately in this theorem we have proved that whenever we have the gradient vector, so in that case curve is depend on endpoints only. So let us consider another consequence of fundamental theorem. If f bar is a gradient field, then first path independent. F bar is gradient field, that means f bar is equal grade f. F bar is gradient, but as we know that gradient is what? That is the vector. So vector, whatever it is, it should be what? Exactly gradient field. So in that case, suppose we have 2 points p0 and p1. So to reach p1 from p0, there are two possibilities along this C1 and along this C2. But when we consider work done along the C1 and work done along the C2, so in the both the case, what we get? Same work done. That means f bar can be written as grade f. Again this is the same. But whenever we do work done on the left hand side, that means if we consider path C1, so again it will be equal to when we work done consider from the C2. So next one, f bar is equal grade f is conservative if C is a closed curve. So first one, what do I mean by closed curve? If the curve has starting and ending point both are same, then the curve is said to be closed curve. So if we consider work done for this closed curve, so always it will be 0. But here it is given that fr is equal grade f, that means fr is conservative. So here you can assume that our previous theorem integration along the C grade f into dr bar. But as we know that curve is depend on two endpoint, so f of endpoint minus f of starting point. But in this closed curve we have starting and ending points are same, so what we get answer 0. So let us consider one counter example. So it's interesting, try to understand what is the exactly vector representation. But here fr is equal minus y comma x. So what will be its line integral? So here contour says nothing but unit circle. That means centered at origin and one radius circle. So in that case, first one, let us understand what are the representation of this vector field f bar. But before that, let us understand f bar is equal x comma y. If we assume that this one point, so this can be written as f bar is equal x comma y. So these are whatever I have represented, this is the vector, as we have discussed in the previous video when we were discussing about the curl and divergence. So you may see that video too. So this is the vector f bar is equal x comma y. But if I suppose to represent f bar is equal minus y comma x, so what will be the representation? But if we consider here f bar as x coordinate, that is only x. But here x coordinate is what? Minus y. But if I compare with this point xy, so here it will be what? Here x coordinate becomes what? That is the minus y. So our points becomes here x coordinate, that is the minus y. And another y coordinate is what? That is x. So y coordinate is here is what? That is x. So we can say this will be point here and direction look like, we can say whatever it is represented here. Any point if you consider from here, so according to that you can represent in this way. So this is what exactly counterclockwise direction. Okay, so here, sorry, this is anti-clockwise, not counterclockwise, anti-clockwise direction. So here we are not going to discuss all these points. We will discuss after completing this example. So here, given that contour is unit circle, so we can represent its parametric equation x is equal cos theta, y is equal sin theta. To get this circle, we have to rotate theta belong to 0 to 2 pi. Here r bar, that is the position vector xi plus yj, but x is equal cos theta, y is equal sin theta. But whenever we represent here dr bar, so it can be written as minus sin theta d theta into I plus cos theta d theta into z. But when we take d theta common, so we have this way. But here our vector field fr is equal minus y comma x, but y is equal sin theta, so minus sin theta I, x is equal cos theta, so cos theta z. But when we assume fr into dr bar, so that means it is required to take a dot product of fr into dr bar. So this is the fr and this is the dr bar. So when we take its dot product, as we know that I dot I, that is 1, I dot j, it will be 0, and j dot j, it will be 1. So here we get sin square theta plus cos square theta into d theta. But this is the identity, so what we get? Only 1 into d theta. But when we integrate over the contour C, but contour C to get, we have to rotate 0 to 2 pi. So whenever we integrate, so answer is 2 pi. That means something we get here work done. Here answer is non-zero. So that means fr is not conservative. Also we can say that it is not a path independent. To have path independent, it must have answer 0. If the answer is 0, that means we can say that fr is conservative. So let us assume this question so it will be clear more. Fy is equal y comma x. Here we have the same unit circle and here direction is counterclockwise direction. So what will be the line integral? Here vector is there as we have discussed in previous question, so we can determine here its parametric equation and parametric equation we can use, and according to that Fy into dr is equal cos 2 theta into d theta. But when we consider this integral, so whenever we put all this value whatever we have Fy into dr, so that is the cos 2 theta into d theta. But when we integrate, so answer is 0. What does it mean? This means Fy is conservative field. In fact, Fy is gradient of some scalar function. So here you should remember that if Fy is conservative field, that means there exists a scalar potential function such that Fy is equal grade f. Again I repeat, if Fy is conservative field, that means we can determine scalar potential function so that Fy itself is what exactly gradient. So here this Fy is a gradient, I say, of f is equal xy. But when we determine gradient of this function, so what we get, that is the, when we assume that our definition, so what we get yi plus xi. So this is what exactly whatever we have assumed in previous question, that is f bar is equal y comma x. This can be written as yi plus xi. So that is the same. So that means if the vector Fy is conservative, that means there exists a scalar potential function so that Fy is written as grade f. So simply we can conclude Fy is a gradient field. Here I am not going to discuss about this concept, how it will be helped in physics. But here I would like to represent only meaning of the conservative. Conservative means no energy can be extracted from the field for free. That means total energy is conservative or conserved. So consider equivalent property. Here Fy is conservative. That means ln integral Fy into dr bar is equal 0. Here curve is closed curve. If this is there, so if and only if ln integral Fy into dr bar is path independent. If the ln integral is path independent, so we can say Fy is a gradient field. If Fy is a gradient field, then we can say m dx plus n dy is an exact differential, that is the df. If anybody asks to you so that line integral is exact differential equation or simply is exact differential, so in that case it is required to consider m dx plus n dy is the vector field f bar from these. What will be here vector field f bar? M comma n. That will be our vector, and that vector field f bar is conservative or not. If the vector field f bar is conservative, then we will say that it is a exact differential. That means we can say ln integral is path independent. Also we can say f bar is a gradient field. But question is there how to show that f bar is conservative. If we have three-dimensional vector space, so in that case we can assume that curl of f bar is equal 0 bar vector. If answer is non-zero, then we can say f bar is not conservative. So here, but when we talk about the two-dimensional, so f bar is equal grade f. So from this I assume that vector field f bar is equal mi plus nj. Grade f can be written as f sub x I plus f sub y j. But when we compare corresponding component, so what we get, m is equal fx, n is equal fy. But here, if we partial derivative with respect to y, so f sub xy, so here it will be my. If I partial derivative with respect to x, so what we get, f sub yx, and here ny. But as we know that fxy, fyx, both will be same. That means this is the same. That means we get here my is equal nx. So here, if we consider conversely, if fy is equal m comma n, defined everywhere, differentiable everywhere, and my is equal nx, then we can determine fr is a gradient field. That is, fr is equal gradient. So this is to for you understand. So let us consider small counter question. This can be asked in your MCQ examination. fr is equal minus y comma x. Is fr is gradient? That means, is there exist a scalar potential function fr, scalar potential function f, so that fr is equal gradient? But here it is not said that determine the scalar potential function. So only you need to follow this one. So if fr is given, as we know that this is the differentiable everywhere, so here it is required my is equal nx. So here what we can say, my, that is the minus 1, n sub x, that is the 1. But we can observe that both have same answer. This is different answer. That means we can say fr is not a gradient. So let us assume that another question, fr is equal this one, and here what value of a vector field fr is a gradient. So here fr is given, so we can determine m and n. So here we can find m sub y and n sub x. To be gradient, we must type my is equal nx. But here m sub y is equal ax, n sub x, that is the 8x. So what we get, a is equal 8.